Hi, so we're going to start out this chapter on the motion of rigid three-dimensional objects, going through energy and momentum methods. So we're transitioning away from just looking at single particles to objects where different pieces of that object have different velocities and accelerations going on. Okay, there's three different sections to this chapter: energy and work, impulse and momentum, eccentric impact. We're going to start with just looking at energy and work because it's the easiest way to solve these kinds of problems. Another way to think about breaking these problems apart, so when you're reading the statement or thinking about the system that needs to be solved, if you're just worried about forces and accelerations, so you have some system, the force is unbalanced and it's creating acceleration, and they say, what's the acceleration of this? Then you would use kind of chapter 16 stuff. If there's some kind of a changing velocity in the system, that's what's happening in this new chapter 17. So you start with this velocity, whether it's a rotational velocity or translational velocity. So you're starting here, but then by the end of it, you have some new velocity, right? And they're describing how that velocity is changing. That's where chapter 17 comes into play. So if you have velocity changing because of force through a distance, so friction acts through some distance, right? It's scraping along 1 foot of the floor, or you're rotating it through 30 degrees that this moment happens. That would be work and energy if you have displacement information. If the problem statement gives you something with time, so you have this velocity and 3 seconds later there's a new velocity, and in that 3 seconds some force was applied. That would be impulse and momentum. So pay attention to those key words in the problem statement to know what method to use to solve that problem. If it just has information about forces, stick with free body diagrams, kinetic diagrams, chapter 16 methods. If you have velocities changing and that change happens through a distance or a change in the angle of the system, that's going to be your energy balance. If the velocity changes and that change happens over a time period, then we will look at impulse and momentum methods. So for this very first section of the chapter, we're going to be looking at velocities in the system are changing, and they're changing because of a force or a moment that happens through a distance or an angle. So we're looking at this middle methodology to solve problems with. Okay, thinking about energy, T, and work. So here's those equations again. We have some initial energy, something changes it, some final energy. This comes from F equals ma, and we're splitting this apart, getting rid of dt dependence. So mv turns into our 1/2 mv squared, and this is being changed by a force through a distance. Okay, so starting energy. And think of this like a movie. So you have some frame in the movie and some initial energy. So we start going 60 miles an hour, and then the brakes are applied through some distance. And at the very end, we're only going 30 miles an hour or something. So any kind of motion that's happening, whether it's rotational motion or translational motion, we're going to add all that together, make sure we have every type of motion accounted for in that initial energy calculation. And then we'll think about the final energy. So maybe it rolled to a stop, or maybe it's speeding up, but we're going to add together any kind of motion in the system going on at some later scenario, and what happens in between those two times that changes that energy, both translational and rotational energy. Okay, if you have an object, internal forces cancel out. We only need to worry about external forces. And where you draw your system boundary, that's going to define what is external to the system and what is internal to the system. And we'll have some examples with that of different ways you can carve up a problem to either get rid of having to worry about things that you don't want to worry about, or if I do want information of something inside of that problem, you can put your system boundary right through whatever you're interested in to solve for it. So carving things up into internal and external forces is part of the game of solving these problems. Okay, work of forces acting on a rigid body. So in our energy balance equation, we're looking at this middle term here. So this is the piece of the puzzle that changes the energy of the system. And we'll look at both changes in the translational motion of the system as well as changes in the rotational motion of the system. Back to work. So translational motion, this is what we had before when we were just dealing with particles. So we have some initial velocity, maybe it's scooting along in this x direction, okay? And the force is tugging up on it. So part of that force is in the same direction as the motion. This is a dot product. So it's not just the entire force, it's the piece of it that's in the same direction as displacement, same direction as velocity. In this scenario, that would be the adjacent side, so cosine of that angle between the force and the direction of motion. But don't just memorize F cosine theta. Depending on what angle you're given and the scenario of the problem, just remember it's the chunk of the force that's in the same direction as displacement when we're looking at what changes the translational motion of the system. So F dr, F dx, F dy. Okay, for a moment. So this is getting into the rotational part. Remember, a moment is created by a positive force and a negative force. So if you have some object and you want it to turn, you would need two forces, right? So if I have one force pushing it this way and one force pushing it that way, the combination of those equal and opposite pairs of forces are going to get this thing to start rotating. For the diagram, so this potato could be anything, right? But you have a positive force going straight up, a negative force coming straight down. If you add those two forces together, because one is up and one is down, they add together to 0. But because they're separated by some distance, they do create rotational motion. And if you look at that in terms of work, and this is a little bit confusing. Okay, so let's say you have some object and it's moving, okay? Maybe it's rotating and it's going forward. So we have three-dimensional motion going on here. It's rotating as well as it's going forward. And then we're going to take two spots on this. Okay, so if I draw two dots on here, we're going to keep track of maybe this wood knot down here and this wood knot up here. Okay, so we got an object and then we've got some little spots on this object. I want to keep track of the velocity and the motion of each of those spots. And the thing is moving forward and it's also rotating. Now we've got two forces that are creating that motion. So if you add up force through a distance, what kind of work is happening there? If you look at this diagram down here, you'll see some interesting things that fall out of this. Let me just grab my laser pointer. Okay, so as it's going forward, that's dr1, this first displacement. So that's the displacement of the thing just moving straight forward. And one of them is moving maybe to the left and the other one is moving to the right. But for these displacements going forward, those end up, the work cancels out because it's positive on one side and negative on the other side. So the translational piece created by these two forces, you don't have to worry about the translational motion. That cancels out. However, there's this other dimension, R2, that does not cancel out. This is the rotational piece of the motion. Okay, so as well as going forward, it's also rotating. And when you look at this rotational motion, the displacement here, R, that change in position is going to be r d theta. So let me see if I can. So remember, if I have a circle and maybe I start with this one angle, so I'm at 10 degrees or something, and a little bit later, maybe I'm at, I don't know, 100 degrees or something. So I've changed what angle I am at, and the distance that has traveled here, usually they give the arc length the symbol of S. That's going to be equal to my radius times theta. This is for a constant radius problem. Okay, so instead of circumference equals 2 pi r, I have arc length is equal to radius times theta. So this little displacement here of r is going to turn into r d theta, both of those things. So we're looking at, this should be an S instead of an R. That's kind of confusing nomenclature. Okay, so now we're looking at the angle that has changed, and the force, this is the piece of it that's a moment is kind of a cross product. So between these two forces, you're going to have a position vector R, and then you'll have the second force F that has created this displacement. So when you're looking at a pair of forces, so you have one down and one up, and then maybe I take the moment around this point over here, and you get the same result regardless of where you take the moment around, but this is the easiest position to show it from. When you take the moment, I'm not having to worry about this negative force because it goes through that point we're taking the moment around. So it's only one of those forces that ends up going into that displacement. Okay, so we have work, instead of force through a distance, we have a moment. So hopefully you can see that moment coming out of it. So you have, sorry, I'm drawing this with my mouse. So moment, force times a distance through d theta, some kind of an angle that is happening here, okay, that is creating the same kind of displacement. So in the end, when we look at the work that is changing the energy, there's going to be two pieces to it. There is the piece from translational motion, and then there's another piece from rotational motion. So two parts to that energy calculation. And instead of looking at like position x1 to x2 for translational motion, we are looking at what angle it starts with, so like 10 degrees, and then what angle it ends up at. It goes to 45 degrees. Only make those angles in radians. Remember, it's not 360 degrees times r, it's 2 pi times r. Keep all of your angle measurements in radians. And the moment piece of it is going to work out very similarly to that translational piece of it. Okay, so I get this final equation up here. We have the translational work that is changing the energy, and we have a moment through an angle that is also changing the, and really the moment goes into change of rotational energy, and this 𝐹𝑑𝑠 goes into change of the 1/2 mv squared, that translational piece of kinetic energy. So you're looking at this piece and then the moment, or if you have two equal and opposite forces, those would only change the rotational chunk of it. So really study these equations and convince yourself of the displacement that moments are creating and how that's going to change the energy of the system. Here's a couple of examples. Do the pin forces at point A do work? Okay, so we're looking right here at point A, and maybe this bar has a weight, and so there's a force going up at point A, right? So you have some kind of a force in the y direction. Does this force do any work? Well, remember, work has to have a displacement, and it's pinned in place at A. So there is no, this piece of the bar at A, it's not moving. It's just rotating. So for this piece, we'll say no, there's no displacement, so there's no work. Okay, how about the force at P. So does this force at P do work? So what do you think? And you can imagine the system right now, and then a second from now, what is it going to look like, right? So the next position, maybe the bar is going to swing up like this, right? And we could quantify that by saying, oh, it's changed by 10 degrees or something, right? And if you want to calculate the moment for that, so remember from statics how you would calculate the moment. So you'd say from the point of rotation to where the force is applied. So we have some kind of a moment that is equal to that position vector. It's a cross product by F. So R cross F, this would be, remember, positive or negative. So clockwise, this is a negative moment. It'd be like screwing it into the righty-tighty, lefty-loosey. Think of a right-handed screw. So if it's being screwed into the board, that would be negative. Okay, so you have a moment, and that moment is acting through an angle. So remember what we learned about work. So work is going to be not just the moment, but the moment through some angle. So if we said that this was like, I don't know, pi over 4 or something, right? Let's keep this in radians. So then we would take this moment and we would multiply it by that change in radians, and that would create some rotational motion, right? So the motion it creates, instead of 1/2 mv squared, we're going to be looking at 1/2 I omega squared in this case. So for this case, the force, yes, it does do work, and it's creating this rotational motion. Okay, so we have moment through an angle, and we have the force. I wish that forces were labeled as F and not P, but this is the force. And H, okay, so H is like the distance away it is from that rotation point. And then we can look at some position A and some position B and see how that angle has changed. And that's going to be the amount of work that was done that is changing the energy of the system, changing how fast it rotates. Okay, here we go. Does the normal force do work on the disk? So it's sitting on the ground, and the ground is pushing up with some normal force. Well, remember, work, it has to be moving in that direction, right? So it would have to have some velocity in the y direction, which it doesn't look like this situation it's going to come up off the ground or anything. It's not moving up and down, it's moving sideways. So because it's not moving up and down, that dot product, it won't work. So there's no work done by the normal force because it's not changing the velocity. It's not moving it. That force isn't. Okay, how about the weight? So here's the weight is coming straight down, and that is going to be, it's the same thing, right? So the weight is also not doing work. Here's an interesting one. If the disk rolls without slipping, does the friction force do work? And initially you think, oh yeah, it does seem like it would do work. Let's talk about without slip. So if it does slip, okay, so if this is like leaving tread on the ground, it's sliding and slipping, then it does do work. And however much tire tread is left on the ground, that would be the distance that force is acting over. But if it does not slip, okay, no slipping at all, it turns out that it does not do work. And there's a couple different ways to explain why this is. Probably the best way is to think of your displacement as being created by velocity through time. And if it's not slipping, the velocity of this little piece of tire at the ground is 0. So if the velocity is 0, there's not going to be work involved in that. And until it starts slipping, that velocity is 0, there's no work involved. What friction will do, so if there is no friction, then the tire wouldn't rotate. If it's like a perfectly icy surface and it could be sliding down with no rotation at all. And then with friction, maybe it rotates. And what that does is it changes the energy from all being in 1/2 mv squared in that translational piece versus 1/2 I omega squared. So the friction will divide up how much energy is in rotational energy versus translational energy. But if you add it all together, it actually does not change the overall amount of total energy in the system. So for friction only does work if it's sliding, if it's kinetic. Static friction never does work. Interesting result. Kinetic energy of a rigid body in plane motion. Okay, so we have some object and it's got some crazy motion. So if you look at the center of gravity, a lot of these problems will reduce to looking at how the center of gravity is moving and then everything else with respect to the center of gravity. For the nomenclature on this, if you see a letter that has a line on the top of it, like a velocity with a line or position vector, that is talking about the velocity, not of this corner over here, because that corner might have a different velocity, but it's talking about the velocity of the center of the thing. So the kinetic energy can be broken into two parts, and that is the translational motion of the center. So maybe the whole thing is going forward, right? So that would be the velocity of the center of this. And then as well as going forward, maybe it's also rotating too, right? So if I want to know what the total velocity of some other corner of this is, it's going to be a combination of the thing going forward and rotating. So if you would add those two vectors together, you add together what the center of the thing is doing, so that's this V with a bar over the top of it, and with what it's doing with respect to the center. So you add those two together to get the overall velocity of the whole thing. So there's a big summation sign here, and you would have to go through each particle in the object, each little element of it, to solve for this. We have two coordinate systems. One coordinate system is the Newtonian frame with respect to the ground. So that's like what we would measure the velocity of the center of gravity with respect to, just the ground. And then all of these individual pieces of the object, we're also going to look at to see how they are moving with respect to the center. This little tick mark above it, so you see r sub I with a little tick mark, that is the velocity with respect to the center of mass. So with respect to the center of mass, so the position vector, the velocity vector, this is all with respect to the center of mass, and then the overall velocity of each individual particle, you can see is a combination of what the center of mass is doing and the velocity with respect to the center of mass. So see how these two vectors add together to the overall velocity of the particle. And this little piece with respect to the center of mass, this turns into the rotational part of your kinetic energy. So we're going to have 1/2 mv squared, where the v is the translational motion of the center of the object, and 1/2 I omega squared, this is the rotation around the center of mass, where this bar above your inertia, that means this is the moment of inertia with respect to the center of this object. So it's the motion of the center of gravity and the rotation around the center of gravity, and those two pieces give you the total kinetic energy. And hopefully that makes sense. If something is just moving forward, that's one kinetic energy, right? But if it's moving forward and it's rotating, there's more energy in that system. So you have to take into account that rotational motion. That's an energy, and it's part of the picture. So this is all with respect to that center of gravity. Okay, so this is, saying the same thing. 1/2 mv squared, 1/2 I omega squared. The bar above both of these is with respect to the center of gravity of the object. fixed axis rotation. Okay, so instead of a frisbee just flying around in the air and the entire thing is moving, let's say we have something that it's actually going to be moving around a peg or something. Okay, so it's no longer moving with an axis around the center of gravity. It's now moving around a fixed axis, and that axis is going to go through some point on the object. Let's call it O. So we have some point O, and the whole thing is now rotating around O. How would we deal with that? Because now it's not rotating around the center of mass anymore. Once again, we're going to have to add up what each particle is doing. And the velocity for each particle, the whole thing is not moving around, so we don't have to worry about the 1/2 mv squared anymore, because we don't have a translational motion of the whole thing, like the center of mass moving from one side to the other. Because that axis is fixed axis, it becomes purely a rotational motion around that fixed axis. So everything on here, the velocity is going to be described by r cross omega. So remember the right-hand rule. If it's going clockwise versus going counterclockwise, omega is going to describe that motion. So v squared goes to r squared omega squared, and that r squared m is going to turn into inertia. This is not inertia around the center. This is inertia around point O. That's a very big different thing. If I'm going to rotate something around the center versus if I'm going to rotate something that's not around the center, the farther from the center you get, the harder it is to rotate. This is a different inertia. It's a different, the summation sign turns into an integral if you're actually calculating the inertia yourself, or you can look it up in tables, and tables will have objects. This is the inertia if it's rotating around this axis versus this is the inertia if it's rotating around this axis. They're two different things. So pay attention to what inertia you're dealing with here. So in this case, it's not the inertia around the center of gravity, which is what you might see in a table. It's the inertia around your fixed axis, around whatever axis it's trying to rotate around. So that's a very different thing. Okay, through the parallel axis theorem, you can equate this inertia through some point O with what you might find in a table. So if you only have the inertia around the center of gravity in a table, that's this I with a bar on the top of it. If you just add what the center of gravity is doing, and what's the velocity of the center of gravity? Well, it would be from the axis of rotation to the center, so whatever radius that is. So r omega for the center plus I, these two terms add up to the same thing as this initial 1/2 I omega squared. But in this case, if you know the inertia around some point O, you don't have to add in this extra 1/2 mv squared. Okay, it is just this 1/2 I omega squared, only around this axis. But if you don't have inertia around the axis, if you only have the inertia around the center of gravity, then you have to have both of these terms in here. Okay, so let's just review the parallel axis theorem so you can see why these two add together to this. So here's the parallel axis theorem, and this is back from chapter 9 in your statics book, if you took it through McGraw-Hill. Okay, so if you have the inertia around BB, so C is your center of gravity, right? So if I rotate it around the center of gravity versus down to A, so if I come down to this new axis A, and now I'm rotating it around this thing instead, okay, what's the difference of inertias here? And for that, let's go ahead and we're looking at r squared m, or y squared dA, the distance from the axis to each element here. And you can split that distance. So I'm going from A to each individual element on here, and we're going to split that distance into how far it takes to get to the centroid, and then from the centroid to each element. Okay, so instead of y squared, we're going to split that y squared into distance to the center and then center to the element. So these two parts. Okay, so let's split that apart. We have y times y, and then y times d, d times y2, yd's, and then we have d. Why would we split this apart? Well, if we have the distance from the centroid to each element, this first chunk of it, this term turns into the inertia around the center. So this is like what you'd find in a table, right? So you have the moment of inertia of what it would be like if it was rotating around the center of the object. That's the inertia with a bar over the top of it. For the other two terms, so this 2d times y, because half of it is above and half of it is below, if it's squared, plus and minus cancels out. But if it's not squared over here, half of these are up, half of these are down. Sorry, that's the center of mass, right? Is you have, it's right in the middle of the thing. So with half up and half down, this one goes away. So it cancels out to 0. And then what you're left with is d squared, which is from the new axis of rotation to the center of mass of the object. And this is where we have the parallel axis theorem. So the inertia around a new axis, so I'm rotating it around the base here now instead. So the inertia around the new axis down here is what the inertia around the center of it is, plus AD squared, or in 3 dimensions, you're going to have mass times distance squared, where that distance is from the axis of rotation to where that center of gravity is. And basically what this equation is telling you is the farther away you go from the center of gravity, the harder it is to rotate. So it's very dependent on r and the distance away. And naturally, an object, if it's not pinned down to anything, it's going to want to rotate around its center of gravity. But if it's pinned in place by something and it's forced to rotate in a different way, then this is going to be how hard it is to rotate. Remember, inertia is it describes the resistance to rotation. So this combination of the relationships between the inertias, that is on the previous slide what translated to these two different kinetic energies. Okay, so if you have I is equal to I plus mr, okay, you can see how these things are related from the parallel axis theorem. So you're either getting the inertia around the new axis, or you have to add these two different terms together to get your kinetic energy. And that comes from, you either just grab the inertia around the new axis, or you have to have two terms because it's the inertia around the old one plus that new distance to get your other kinetic energy. Okay, so here's a couple of examples using the parallel axis theorem, and you can look some of these shapes up in tables. So like if you're going to go around the center of the circle versus maybe you're rotating around the edge of it instead, what would that look like? So the inertia, if the whole thing was rotating around this T line, would be what it is around the center. So this is what you would look up in a table. And then your area times distance squared, so this is the area of the circle, pi r squared. And in this case, from the new axis of rotation to the center, that ends up being the radius of the circle. So you can add those two together and see how much larger the inertia is to rotate around a tangent line versus rotating around the center of mass. So 1/4 versus 5/4. That's quite a bit harder to rotate around that tangent. Here's the same thing for a triangle. So again, you can look up in the table quite often what it is around the centroid. So for BB, this is the centroid axis. You can see that line on top of it that's talking about inertia around the center. And if I want to rotate it around this new axis, AA, so down here on the base, then it would be a combination of what it is around the center plus AD squared, where D is, some distance. For triangles, the centroid is 1/3 of the way up. So, okay, so there's a couple examples of there. Plane motion, we've got fixed axis is going to be 1/2 I omega squared if you know the inertia around that point. equivalent to using around the center for the velocity of the center of gravity. Okay. Yeah, so here if you plug in inertia around a new axis is what it is around the center plus mv squared, you can see how that translates to these two things being equivalent to one another. Concept quiz. Here we have a solid cylinder and a pipe. Same diameter, same mass, both released from rest at the top of a hill. What will reach the bottom first? Okay, give you a couple of seconds to think about that. Who will reach the bottom first? So we have MGH. They start with the same potential energy, and that potential energy is going to turn into 1/2 mv squared and 1/2 I omega squared. So it's the same amount of energy, but some of that energy goes into translational energy and some goes into rotational energy. Which of these is harder to rotate? If I look the inertias of these objects up in tables, which is harder to rotate? The pipe is harder to rotate. This one is mr squared. The entire mass is way far away from the center, okay? Hard to rotate, easy to rotate. So that means when it starts rolling, more of that energy is going to get sucked into the I omega squared chunk of it instead of the 1/2 mv squared part of it. So here we go. A will reach the bottom first because A is easier to rotate. Easy to rotate, small moment of inertia means that more of that energy is going into the 1/2 mv squared instead of energy getting sucked into the 1/2 I omega squared. Okay, so larger inertia, more energy to rotate it, more energy sucked into rotational motion. They both have the same amount of energy at the end. Okay, so which will have the greatest kinetic energy? If you add 1/2 mv squared plus 1/2 I omega squared, if you add both of those pieces together, translational plus rotational, they add together to the initial MGH. They both add to the same number. But how much is in rotational versus how much is sucked into translational energy, that's what's going to control which one reaches the bottom first. So the one with the largest translational energy will reach the bottom first.